Hey guys, Mr. C here. In today's video, we're going to derive the kinematics equations using a velocity versus time graph and the concepts of slope and area. So remember, one of the major points we've been talking about is all the kinematics concepts, displacement, velocity, and acceleration, can all be found from the various graphs using the idea of slope and area. If we're given a velocity versus time graph, recall that the slope represents the acceleration of the object, and the area between the graph and the t-axis represents the displacement of the object. So what we're going to do today is we're going to analyze an arbitrary velocity versus time graph, find the slope and area of that graph, and use it to find the acceleration and displacement equations. So consider the following. Consider a velocity versus time graph for the following scenario. An object starts at rest and undergoes a uniform acceleration. Well, we know if it starts at rest and undergoes uniform acceleration, then the velocity versus time graph looks like a linear straight line. So let's start the problem at some place along the time axis. We'll call that place just a little dash for 1, and we'll end at some other time. And the time from the 2 dashes will be our time in this case. Then, at the first instant, the object had some velocity, which we're going to call the initial velocity, and then sometime later, at the end, it had a final velocity, which we'll call Vf. So first, what we're going to do is analyze the slope of this line. So recall that slope, is delta y over delta x, or we all know it as rise over run. In this case, it's how much did we rise? It's the Vf minus the Vi divided by the run, which of course is the time. Now, recall we'd said above, the slope of velocity versus time graph represents the acceleration. So that means that the acceleration of an object is Vf minus Vi over t, and if we want to rearrange that, we can say, well, Vf minus Vi, that's just the change in velocity divided by time. Or if we wanted to solve for one of the velocities, we could cross multiply, set the acceleration over 1. We get something like AT equals Vf minus Vi. So therefore, Vf equals Vi plus A. And that is usually the most commonly known version of the velocity for our first kinematics equation. So now what we're going to do is we're going to, instead of finding the slope of that graph, we're now going to go ahead and find the area of that graph and use it to figure out the displacement of the object. So for this graph, the area looks like this. I'll shade it. And recall, when we have a weird trapezoid-like thing, it's best to break it up into 2 pieces. So what I'm going to do is I'm going to break region 1 up into a rectangle, region 2 up into a triangle. And so finding the displacement really amounts to finding those 2 areas. So for the rectangle, recall, area is base times height. So this area is Vi times t. And then above that area is 1/2 base times height. So area is 1/2 t times the height is the Vf minus the Vi. And then the last piece is, if we go over to our first kinematic equation, remember that Vf minus Vi actually equals something. Vf minus Vi is the same thing as acceleration times time. So what we're going to do is we're going to replace this Vf minus Vi as simply acceleration times time, because the 2 are equal. So what does that mean? It means that the displacement of an object is Vi times t plus 1/2 acceleration, if I have 2 t's, times time squared. And there is our second kinematics equation. Finally, there's one more kinematics equation, and that is the Vf squared equation equals Vi squared plus 2AD. First off, its usefulness. It's really an awesome equation to use when you're not given the time in a problem, because it only depends on your velocities, acceleration, and displacement. Now, where this equation comes from is as follows. Taking our original equation, the first equation we got, Vf equals Vi plus AT. If we solve for t and then plug it in to both pieces of the equation, that eliminates the t variable and gives us an equation all in terms of distances, initial velocities, accelerations, and final velocities. That's through about 7 or 8 steps of math how this equation pops out. So there's our 3 kinematics equations. We're going to use them a bunch in class. Hope you guys have a great evening.